Hi, welcome to question 2. First, before we jump into part A, let's look at a little bit of review on Dijkstra. So Dijkstra takes in this case, two things. It's always going to take in a start vertex. The start vertex is the vertex inside your graph that you want to run the Dijkstra algorithm at. And then in this case, we're also passing in the graph itself. The return value is going to be two arrays. We have a dist array, which holds the length of the shortest path from the start vertex to that particular vertex. Remember in graph.java in lab 19, when you implemented the shortest path method, your index into the arrays represented or corresponded directly to the actual vertex because the vertices were integers. And then the prev array is another return value, which is going to hold the predecessor, the immediate predecessor, on that particular vertex's shortest path from the start vertex. Okay, and the reason why we have this prev array is because in order to actually trace the shortest path, we need to know what were the nodes along the shortest path, right? Okay, so let's actually examine the pseudocode. For a complete run through of the Dijkstra algorithm on an example graph, you can look at the mini lecture on lab 19. But for now, let's just parse the pseudocode and see where all these functionalities are being used. Okay, so the first part is implementation. So for each vertex in our graph, we want to initialize its distance to infinity. And the reason we initialize it to infinity instead of another value such as negative infinity is because remember in Dijkstra, we only update the length of the shortest path if the new length is better than the original current length in the priority queue. Right? And so if we have this distance initialized to negative infinity from the start, for example, then negative infinity is really the best that you can get, right? It's really the smallest possible length that you can get, although negative length doesn't really make sense. And so if you have negative infinity, then you'll never update, any of the vertices. And so it's necessary that you update it with the worst possible length, which is infinity. And then for the prev, you're going to have it be undefined because, again, we haven't really started running the algorithm at this point. Then, because you know that you'll be starting at the start vertex and the S is going to be the first vertex you pop off from the priority queue, you want to initialize its distance to be 0 specifically, which is going to ensure that when you first run this while loop, the very first vertex you're going to look at and visit is going to be the start vertex itself, okay? Because its distance 0 is smaller than infinity. All right, so next we initialize the priority queue. So Q stands for the priority queue. What is a priority queue? Remember that it is basically a queue, but it orders the elements inside, in our case, the elements or vertices, based on their priority value. So what is our priority value? The priority value is going to be the length of the shortest path. And so the node with the smallest priority value is going to have the highest priority in our priority queue, right? In other words, we want to remove the min first. And so that's what happens in this line when we remove a vertex from Q with the smallest distance. And so in the very first iteration of the while loop, U is going to be equal to the start vertex. And then afterwards, it will depend on our graph. Okay, so remove min and then make sure that its distance is not actually equal to infinity because otherwise, again, all of its, if its distance is infinity, then if we run this, right, without breaking, then all of its neighbors is also going to have their distances be equal to infinity, and then nothing will ever update itself in the algorithm, right? So we always want to start with something that's not infinity, which is exactly the start vertex. And so for each neighbor of the start vertex and also any other vertex in the other iterations of this while loop, you're going to look at the distance from S to this current U plus the distance from U to this neighbor V. Okay, and if this new distance, this new shortest path distance is actually less than, better than the current distance for V, then you want to update. Right, so you want to now set the distance for V to be this new distance, and now its prev also has to be updated to U. Okay, and so by updating the predecessor, you're able to, once you terminate from this algorithm, trace back the actual shortest path that led to V from S. Okay, and that would go through U. All right, and then you repeat this until the queue is empty, and at that point you will return these two return values. Okay, so for part A, we have these 5 functions: enqueue, dequeue, isEmpty, contains key, and update. And the question is asking how many times do we call each of these operations in one complete run of the algorithm? Okay, well, what is enqueue? Enqueue is adding something to our priority queue. So how many times do we call enqueue? Well, really, the only time when we add to our priority queue is in the very beginning, in the initialization stage, right? We add all the vertices, so that means that we're running the for loop v times, which means that we're calling enqueue v times, right? So let me actually just notate that this is the enqueue operation. Okay, so we're going to be calling this v times, and I'm just going to say at most v just to be just to have it in terms of runtime. And I say O, big O instead of theta because big O is a looser bound than theta, right? So you could say theta of v, but I'm just going to put it in looser bound of O of v. Okay, and then for dequeue, in this case, dequeue is going to be removing something from our priority queue, right? So when do we remove stuff? We remove it in this line. This is our, or more precisely, this line. But these two are our dequeue operation. We remove the min specifically. So how many times do we do that? Well, we remove one node every iteration of our while loop, and we repeat our while loop as long as queue is not empty. And we know that by this point, after we've done all of our enqueue operations, queue has a total of v vertices. So that must mean that we're doing dequeue v times. Okay, and these absolute value looking things right here are representing cardinality, so the size of our set v of all the vertices in our graph. So basically the number of vertices in our graph. Okay, and now isEmpty. isEmpty is going to be precisely this while check, this while condition. Okay, so how many times do we run this condition? Again, every iteration of the while loop, which is a total of v times, we call isEmpty. What about contains key? So where do we call contains key? Well, let's think about this. Why do we want to check if a key exists in our priority queue? That's because we want to access that key value, right? What is a key in our priority queue? The keys are basically the vertices, and the values associated or mapped to each vertex is going to be its priority, its priority value, which is in this case the length of the shortest path, right? So that happens every time we want to see, every time basically in this for loop, right? For every neighbor of this current vertex, of this current remove min vertex, right? I want to travel to all of its neighbors and then see whether its current key value, so its current length of the shortest path, is worse than its new length of the shortest path. Okay, so in order to actually do this updating, before I actually update, I need to first check whether this vertex even exists in my priority queue, and then I need to get its value and compare that value to the new value that I have. And if the new value is better, then I need to update. So really, the number of times I call contains key and the number of times I call update are exactly the same. They happen in the same for loop. And the for loop is really going to travel every edge in our graph, right? Because we're looking at for each neighbor. And so if I have a vertex here and its neighbors are like this, right? That means I need to travel a total of 3 edges, right? And for each of these vertices, for let's say this, right? Maybe it has 3 more neighbors. So in that case, I need to travel 3 more times. So basically the number of iterations, total iterations for this for loop, among all the iterations of the while loop, is going to be equal to the number of edges in our graph, which means that we're going to be having E as our answer for both these operations, okay? And so maybe one question you might be having is, okay, well, why is it a case that sometimes a key might not be in our priority queue? The reason is because we remove things, we dequeue things, right? And so at some point, we might be going across all the neighbors of a vertex, and maybe this neighbor was already visited at some previous iteration, and so now it's no longer in our priority queue. In that case, we don't need to update anything for that vertex. It's already fixed. Its shortest length is already fixed, okay? All right, and I'll continue B in the next video.